So, heating curves. Unit 4. So this is the first time we're taking notes in Unit 4, so 11.1, heating curves. So, what we're going to do is I need everybody to take the periodic table. I need you to turn it over, and you'll see some knowns and constants in the bottom right hand. Now, I want you to take your brand new piece of paper, and I want you to turn it sideways, and I want you to draw this graph I'm about to draw as big as your paper, okay? So, I want you to take your piece of paper and turn it this way, and I want you to draw this graph as big as your piece of paper. So, we're going to draw the heating curve for water. And in about 5 minutes, you're not going to remember that the freezing point and also the melting point for water is 0, and the boiling point is 100. But you know that, right? In a minute, you'll have to compile that information. Please remember it. But anyway, I'm going to make this 0 degrees Celsius. I'm going to make this 100 degrees Celsius. Now, ice can freeze, you know, well below whatever the scale of this is. This is probably going to be like -20, but, you know, you can have ice, you know, much colder than that. But just because we don't need all that, right? So, what we're going to do is this heating curve, the picture that I just showed you, this picture has 5 legs. And we already talked about the flat parts being phase changes, and then the parts that are angled with a positive slope are where things are actually getting heated because the temperature is changing. So, were you guys okay with that? Yeah. All right, so here we go. This is our first, oops, I went above 0. This is our first leg, and it's actually going to be heating ice. I'm going to draw this next leg. Give yourself a lot of room. Okay? And this is going to be melting. Okay? And then I'm going to have heating water. And this is boiling water or vaporization. Notice how this segment is longer than that segment. This is on the test. I'm going to go ahead and tell you a question. Notice that this is heat, by the way. This is heat added. And that's going to be in joules, of course. There's more energy needed to boil water or vaporize things because you have to overcome the intermolecular forces. You have to overcome the hydrogen bonds in water, for example. They're stuck together, right? I just showed you how the magnets are stuck together. Do you remember what I'm talking about? You have to overcome it. I'm going to write that down. And then this part is heating the gas. So we're going to label that now. So this part is heating a solid. That happened in first period. Somebody said that the answer should be heating ice, and somebody else said it should be heating solid. And they didn't understand how those are the same thing, but they are, right? Because ice is a solid. That was my morning. Y'all, I'm not kidding. I wish I was kidding. Anyway, this is melting. It was a lot of fun. This is melting.
You get a lot of things done in that class.
This right here is, and like Adam so intelligently pointed out, this is heating liquid, which is liquid water in this case. But you have to understand, like, we can also draw the heating curve for carbon dioxide. We could draw the heating curve for iron. So this would be solid metallic iron, and this would be boiling iron. This would be heating liquid molten iron. So it doesn't have to be water, so that's why I'm using different words. But you have to be able to, you know. Anyway, so this is water, though. And then here, vaporizing, which is another word. That's an O. Vaporizing water. I'll write it better. I can do better. I expect great things from myself. And so this is vaporizing your liquid. I did tell you the nice things about yourself.
I don't.
I'll tell you anytime you want to hear, but just not right now. This is vaporizing liquid, and this is going to be heating a gas. Heating gas. I'm going to move my melting to the other side because I'm going to write what happens when you go the other way. So far, so good?
So far, so good.
Flat parts and phase changes. Okay, we're going to keep adding to this. So write kind of small because I'm going to keep giving you stuff. All right? Like I'm going to have to start a new paper and give you more information. But if we have it all here, it helps it make it more sense. So what if I was to go this way? This would be cooling gas, right?
Mm-hmm.
And this is called condensation. Condensation is where you make little water droplets, like on the side of your cup when it's cold and the air is warm, like in the summertime in Georgia. Right? Okay. This right here is cooling liquid. That's a Q. Okay. All right, Pen, just do whatever you want. And when we have freezing, that's also called, so this phase change is freezing and melting, but it's also called fusion. So freezing, and like I said, this phase change is also called fusion. So this flat line is called fusion. And then this would obviously be cool in the solid. Anybody sad yet? You okay?
No, I'm not sad.
Fusion is F-U-S-I-O-N, fusion. So what I want you to do is take a few minutes, and I want you guys to answer on the paper that we're going to finish the notes here in a second. So you have a lot of room on here, but I want you to use this. Now this is the heating curve for water. On your worksheet that you have that you're going to do, you have the heating curve for, I don't know, I think it might be carbon dioxide or some kind of gas, I'm not really sure. But the numbers are different. So different substances have different temperatures where they vaporize or where fusion happens, okay? So your paper that you picked up on the way in the door, do the left-hand side with a graph like this, and then we'll come back and add more to this, okay? I want to make sure you understand what this part is first. So in our heating curve, we have 5 segments to the graph. 1, 2, 3, 4, 5. And I just explained to you what each of those are. The flat ones are changes in phase. Does any temperature change happen along segments 2 or 4? No, so guess what? If I use that Q formula for that, then that's going to be 0. And what's Q going to be? Nothing, because you multiply them together. Do you understand what I just said? Cool. So you can't use that formula for 2 and 4. You actually use something that's a lot easier. So if you look at your periodic table on the back, there are 5. Oh my gosh, how many numbers are there in that chart?
1 million.
5. Do you know why? Because there's 5 sections to this chart. So what I'm going to show you is which number goes where. You already know where some of them go. So section 3, where I'm heating water or cooling water, this is your old friend 4.18. You telling me to, are you okay?
I was saying what up to 4.1.
Oh, I thought you said hold up, and I was like, which part? You don't want to get it.
No.
So, is the temperature changing along on segment 3? Is the temperature changing?
Yeah.
So guess what formula I'm going to use? You just did it. Yeah. So the formula you're going to use is Q equals mass times specific heat delta T.
Yeah.
I mean, you just did that. You okay? All right, cool. So let's look at another number. So the 2.09 joules divided by blah, blah, blah. So that's here. I'm heating up ice. So here I'm going to stick with my colors. That'll make me so much happier. Simple things in life. So here I'm going to use 2.09 joules divided by grams times degrees Celsius. And is the temperature changing? Yes, so I'm going to use the Q formula again. If you can't remember that, look, okay, watch how I'm going to draw the letter Q. Are you looking? Are you looking? Are you looking?
Yep.
See the little slant? If the line's slanted, you got to use Q because it has a little slanty leg. I made that up. It's pretty good. Act impressed.
It's just the opposite way though.
Thanks. But you know, if it was a cooling curve, it wouldn't be the opposite. So that's the thing.
Yeah, that's true.
Yeah. All right. So there's one more slanted part. That's number 5. And here I'm going to use, guess what? The same formula. Q equals mass specific heat delta T, because it's there's a temperature change. And then the value value for the specific heat capacity of steam or water vapor, it says gas here, is 1.84 joules per gram times degrees Celsius. That looks kind of messy, so. Is that the worst thing that's ever happened to you?
No.
You've already been doing this, yes. Alright, now, the flat parts, I can't use those values. So, look at your paper, and it has something that looks like this, delta H. What does delta mean, first of all? Change. And do you remember, does anybody remember there's a fancy word for heat? And I was like, we're going to use that later. It starts with an E. Enthalpy, you're so smart. Enthalpy is abbreviated H. It's fine. It's cool. So the delta H means change in enthalpy, so the amount of heat basically for a phase change. And the fusion is for this line, not line number 2, and the vaporization is number 4. Now, remember a minute ago how I told you that vaporization needed more energy? There's mathematical proof that that's true. To freeze or melt 1 gram of water, it takes 334 joules. To boil 1 gram of water, it takes 2,257 because you have to completely overcome the intermolecular forces, which is a test question. Okay. Anyway, so what I'm going to use, I wanted to tell you what that meant. What I'm going to use here is I'm going to use this value, the delta H of fusion, and I'm going to use 334 joules per gram. Do you see how there's something missing there? Do you see how this unit, what's it missing? Which makes sense because the temperature ain't changing. Oh, are y'all being sweet today? Oh yeah. Okay, so this one is the enthalpy of vaporization, and that is, you're going to use 2257. And that's joules per gram. Let me kind of sequester this off.
Whoa.
I didn't mean to do that, to be honest with you, but yeah. We have I'm going to show you what to do with that. It's actually really easy. So, let me show you how to use this number. So let's just pretend we had 17 grams of water. And I wanted to see the energy needed to boil or vaporize. We'll say vaporize because that's what it's going to say in the test. Okay, I'm really proud that I made this up. I'm just going to tell you. Do you see how that's the flat part of the line? That's line segment number 4. So when you get to when you have Q, right, you have the slanted part of the line. The flat part of the line gets a flat math problem. So you're going to go 17 grams over 1. And then did you notice how it had joules on top and grams on the bottom? Joules on top, grams on the bottom? Yeah. See how grams cancels and I'm left with joules? That's all you have to do on the flat parts. That's pretty sweet, right?
That is sweet.
Very easy. So the flat parts, you do a flat math problem. The slanted parts, you do the Q, and the Q has a slanted leg. Now, what's going to happen to you is, how about instead of just this, I don't know what that was. So here's what's going to happen. When you start a problem, do you know how sometimes I tell you what to do, and the people that do it do really well?
Yes.
So when you do these problems, what it can happen, let me explain what's going to happen. So they could give you like water at negative 47 degrees is heated to 99 degrees. What's the amount of heat needed? So that involves this leg. That involves this leg, and this leg. You got to do 3 math problems. Now, I don't remember what numbers I just made up. Let's just say negative 30 to 99. Your temperature change for this first one ain't 30 plus 99. It's only 30. Because this leg only goes up to 0. Do you see what I'm saying? Then you're going to do this leg. And you're just going to multiply real quick. And then this leg is going to be temperature change from 0 to 99.
Oh. So
for however many legs your temperature range touches, that's how many math problems you about to have to do. And then, of course, what you're going to do when you're done, add them up. So you ready to try it?
now we do number 2 ourselves.
No, number 3, you can just say it's possible. So I'm going to do a problem for you. So here's your example. Example 1. Hi, Hannah, you haven't missed anything.
Just like
No, I'm not serious at all. How many joules of heat are needed? We're getting recorded to I'm just going to put how many joules are needed. So you should put this on your notes. Are needed to heat 17.2 grams of water from, we'll go negative 30. Y'all got to realize that negative part of the graph below 0 could go much lower than 30. Second period thought that meant that as cold as water could get. No, baby. 30 degrees to, let's go 127 degrees Celsius. Okay. The first thing you got to do is look at your graph. And so you're not going to have that picture that you just drew. So look, it's 2 flat parts and 3 slanted parts. Slant, flat, slant, flat, slant. Okay, so basically, how long did that take me to draw it? I'm having a psychic vision in about a month of you coming up to my desk and me being like, where'd you draw the picture? Oh, I didn't. Well, I guess that's why y'all don't like this was going to happen. Okay, so anyway, I'm starting at negative 30, so I'm going to label that, like I'm starting here. Okay, and then 127 is right here. So I'm about to have to do 1, 2, 3, 4, 5 math problems and add them up. Okay? Do you understand how I figured that out?
Yep.
Cool. So let's get started. And I'm just gonna call it 1, 2, 3, 4, 5. So here's leg 1. So this is warming ice. That took me 5 seconds to write. That will keep me from screwing up, so I'm going to do it. So, do you see how this is a slanted part? What formula am I going to use?
Q.
Q. So, Q is equal to the mass of water, which is 17.2, right? And then the specific heat of ice, be careful, is 334 joules. And then the temperature change, I want you, all of you, I want you to think about the temperature change. I'm going to pick somebody. I believe in you. What's the temperature change, Anissa? So I'm doing this leg, right? So I'm going, on this leg, I'm going from negative 30 to what? That's what you're going to screw up. Okay? That's okay. That's why I'm doing this. Yes. On this, the specific heat of ice. Because it's ice at this point. Oh, oops.
Yeah.
I'm just kidding. I'm so sorry.
I was so
No, that's my bad. That's mine. Casey, come get a ticket.
You straight.
I'm so sorry. So, yeah, the specific heat of ice is 2.09. But you know what? In a minute, what I have noticed, because my units don't line up, yes, they're in the sink. And then the temperature change is 30 degrees. So then I'm going to multiply that, and when I do that, am I going to be done? No, I'm going to be 20% of the way done. Yay! Everybody's super excited about this. This isn't hard, though. Like, it's not hard.
It's just so much work.
Yeah, it's okay.
And then if you mess up on one thing, you get it wrong.
Yeah, pretty much.
And then you fail the test.
Shh! Don't be so dramatic.
And then you fail. And then you go into clinical depression.
Stop it, stop it. Alright, did y'all get this? Get this? I'm going to do the next leg, and then you got to figure out the rest. So,
Wait, is that it?
that's 1,078.44.
That's a question.
What? be all right. It's J. Okay, so on the next leg, section 2, what is occurring? Please tell me what's happening on leg 2 of this graph. And I'm not going to ask you, babe. Nikhil, what's happening on leg 2? It's melting. So now I'm going to use the delta H, or basically the enthalpy of fusion, delta H of fusion. That sounds really fancy, but it's just an H and a F, U, and an S, right? So, leg 2. Whoops. I got to make that going. Whee! Okay, whee! So, leg 2, I'm going to take the 5 seconds to write melting. And so, it was 17.2. 17.2 grams. Since it's a flat part of the graph, I'm going to use flat lines.
Yeah.
And then the enthalpy of fusion is 300. This is. I don't know what I did. 334 joules per gram. And then grams cancels. And I'm going to multiply these numbers together. No, because look, do you see how it's written joules and then a line and then grams? That's what this means. You could put a 1 down there, but I wouldn't. Because that's just going to confuse you.
240 or 2004.
No. 5,700.
Do my calculator.
44. Y'all are making me laugh.
Oh, it's 17. See, I put the.
It's okay.
My paper's turned in the 1. Right
No worries.
So
this was leg 2. Okay, so guess what you can do now? Try leg 3. Ready, go. But you don't want to? Sorry. It's not, hush. Alright, leg 3's right here. Warming up that water. So Hannah, you can do this part. Yes. I'm going to come help you, honey. I know you just walked in. It's not funny. I'm so sorry for you. At least you came in. I was videotaping it for you. Okay. So, what's happening here? Like, yeah. So, this is, we did this yesterday. We felt pretty good about it. I mean, like, this is like warming ice and then melting, warming a liquid, and then boiling, like this way. Okay, so that's special. Now here's the numbers on the back of your table right here. So look, anytime the temperature is changing from 1, 3, and 5, we're going to use the heat formula and do it. The thing is, speaking of ice, it's different. So you got to use different cues. So right now I'm asking you to find the cue for that graph. But it's okay. So I'll go back and say, but the bottom line is, the only thing you don't know how to do
gas cannot
is this
boil.
part that's flat.
At 127, it's
It boils at 100. 100 is right here.
And then
This is
you just
gas.
take the mass and multiply by this number. And then like
When it
right,
boils, it
I'm
turns
trying
to
to
gas.
take the mass and multiply by that number. That's all you need. Yes, please. So I'm gonna keep working this one out. So right now I'm on like 3, which is this one. Alright, how'd it go? If you got it, go ahead and go on the floor. The temperature change.
The temperature changed 7,000.
Okay, hold your horses. What is the temp? We're doing leg 3. What's the maximum temperature change for leg 3? 100. It does not matter. Yeah, I did tell you that because we have to do one segment at a time. Remember how this one was only 30? And this doesn't change. And then this is 0 and this is 0 and that's 100. Like, because water freezes at 0 and boils at 100. Okay, so the temperature change change delta T gonna be 100. So 17.2 times 4.18 times 100 give you 7,189.60 joules. Did you get that?
Yes.
Now on leg number 4, leg number 4 is really chill, right? So it's flat part, you do a flat math problem. Go for it. So leg 4 is vaporization. If you don't know where to start, start there. So Hannah, look. See how I have the mass over 1? When you put the next value, the enthalpy of vaporization, that's what delta H means on your formula sheet. See that little delta and then H and then vaporization? Do you see how the units are 2257? And see how grams cancels? And I'm left with joules? Look. Grams. So I'm done. That's all you got to do on the flat part. Really chill.
What are you talking about?
Alright, did you guys get this? Max, take your headphones out. Do leg 5. Thank you. Now, just in case you're still struggling, what's the temperature change for leg 5? Yeah. What did he say? So, Hannah, the only other thing you missed is like the temperature change from this. See how it's negative 30 to 127? At no point can you do that whole temperature change. Like on this, I had to do 5 math problems. So, like the temperature change from negative 30 to 0 has to be this line because I have to do this leg first. So this is going to be 30. That's the quick slash like I did. This is 0 to 100, so the temperature change here is 100. And then leg 5 is 27. Okay, so that's the only tricky part. You got to make sure you're careful on your temperature changes. We're about to do more of these. Don't freak out. So leg 5, it's slanted, so I'm going to use the Q. What was the temperature change?
That's such a big and bulky.
27. What was the number I made up?
This is nice and smooth.
Okay.
I'm gonna start reading my
Show me like you. Yeah, like 50 or 39. I should hold on. See, I know. It is like 7.
That's very
We gotta get this eraser out. This eraser.
I did it wrong or what?
you rounded it.
Yeah. Okay. Are we done?
No.
No, what do you have to do with all these numbers now?
Add it all together.
You have to add them all together. So now add them all together. Now, I will let me tell you something. You're not gonna have to do all 5 legs on a problem probably. So what you're gonna have to do is figure out like 2 or which 2 or 3 you're doing. So that's why you gotta draw the graph first. So everybody adding? Do you see how I can definitely see what my answers are and I can read it and know what I'm doing? Please make your paper look like this with units and stuff. Yeah, no, that's fine. I'm about 100 off, man. On this one?
Yeah.
The delta C is not 127. No, because that leg of the graph, this leg of the graph is only this part, so this part is 100. Okay, as I was adding them up, I had to answer a question and I forgot where it was. So what do y'all get?
I got
Go ahead, Cassie.
5, 3, 6, 8, 7, 4, 7, 6.
5, 3, 6, what?
8, 7. 7.
Good enough. Thanks. Jules, did y'all get something like that?
Yes.
Cool. So did you get it?
Yeah.
Okay. So what I want you guys to do is
Hold it back.
no hush. Love you, but you are going to do the back. But please listen to me first. Like hang with me. 4 through 6 are pretty fast, and then what's going to happen on 7, 8, 9, 10? They're going to make you like check stuff. Okay. So for me, just kind of mark out 7 through 10. Just, we're not doing it. But do 4, 5, and 6. So mark out 7 through 10. And then on 11, what 11 is doing is it's breaking it into the parts so you know what to do. Be careful on the delta T. That will be what you mess up. And then try 12. So you're doing it basically 4, 5, 6, 11, and 12. Okay? And go. I'm going to have your secretaries come up. Have your secretaries written on the board today? No. So Adam, your group is going to do 4. Y'all are 5. Y'all are 6. Y'all can be 11A, 11B, 11C, Katie, 11D, and then we'll go, I'll do number 12. How about that? That's everybody. So pay attention. 4, 5, 6, 11, and 12.